Okay, so moving along to the next topic in 6.2. So this will be kind of 6.2 part 2, I guess. We're going to deal with linear density. So we'll say we're going to generate total mass of an object from its linear density function. So basically, if you know the density of an object and you know how the density changes linearly, either along the x's or the y's or whatever, we can set it up as an integral and integrate along the density function, and that'll generate the total mass. So our equation for this will be total mass, which we'll call m. This will equal the integral from a up to b of rho of x dx. And we use the symbol rho of x, that will be our density function. So as long as I tell you the density function, these types of problems are pretty straightforward. So we'll do example 4 here. So what this says is we want to find the total mass So find the total mass of a 2 meter rod of linear density they give us the function rho of x equals 1 plus x times 2 minus x. Units are kilograms per meter, where x is the distance from the end of the rod. So basically we got kind of some sort of cylinder here. Oops. Probably could have drawn that a little better. We got some sort of cylinder here. The density function tells me as I move along the cylinder from one end to the other end, the density function tells me how the density changes. So I'm going to set up my integral starting at 0 at one end of the rod, and since it's a 2 meter rod, we'll stop out here at 2 meters. And basically what we'll do is we'll just set up integral from 0 to 2 of the density function, which is 1 plus x times 2 minus x dx. This is the equation we want to integrate. I think this is going to be easier to integrate if we go through and distribute the x. So we'll have, this is the integral from 0 to 2 of 1 plus 2x minus x squared dx. So kind of separate the problem statement from what we're doing here. So we got, we're going to integrate along from 0 to 2. They gave us the linear density function, so we just do 0 to 2 of the linear density function. Integral of 1 becomes x. Integral of 2x. X will integrate into 1 half x squared. 2 times a half is 1. So we get x plus x squared. And x squared will integrate into, or negative x squared will integrate into negative 1/3 x cubed. So we want to evaluate that from 0 to 2. So we're using fundamental theorem of calculus part 1. I substitute 2 into this function. And then I subtract it with 0 plugged in for the x's of that function. This all, if you look through it, this all is just going to become 0. And this part here, this will become 2 plus 4. This will be 8 times 1/3. That'll be minus 8/3. 2 plus 4 is 6, so we have 6 minus 8/3. We'll need to multiply this by 3 and divide it by 3. This will be 18/3 minus 8/3. 18 minus 8 is 10/3. And the unit on this is total mass that we calculated here. So this right here is total mass. So the total mass, since the linear density function was in kilograms per meter, the total mass is in terms of kilograms. So this right here, 10 thirds kilograms, that is our total mass. That'll be the total mass based off the density function. So the next bit we have is going to be one that's dealing with the radial density function. Basically, if you kind of consider like a city or something, where here's the center of the city, and you have all these kind of rings about the center of the city, you'll find that as you get closest to the center of the city, we have like a high density there, I guess we could say. And then as you get to like lower and lower and lower rings, as you move away from the center of the city, you get lower population density. So when you're close to the center of the city, you have your high density stuff there, and then as you scoot away, you get lower and lower and lower, is the way that most cities work. So we get this equation that says if you want the population, we'll say P within a radius R, that will equal, you integrate from 0 up to R, sorry, there's a 2 pi in front of this because it's radial. So we get 2 pi integral from 0 up to R of little r times the density function with respect to the radius dr. So this is our radial density function. So for our example, we're going to say the population of a city has a radial density function, and they give us the function. So we'll say the population of a city has radial density function and we're going to say that that radial density function is rho of r, which equals 15 times 1 plus r squared, all that to the -1/2 power. In this we say little r is the distance from the center of the city. We'll say from city center. Okay. Rho has units. Of thousands of people per square kilometer. So we'll say 1,000 per square kilometer. That's the units of rho. And we want to know how many people are living in the ring between 10 and 30 kilometers from the city center. So how many people living in the ring between 10 kilometers up to 30 kilometers from the city center. Okay, so we're going to be asked to calculate a radial population density. So instead of starting at the city center here at 0, so instead of going from 0 up to r, our limits are going to start at 10 and go to 30. So we're going to have the integral from 10 up to 30. The 2 pi is out front, so we have 2 pi out there. And then we have r times our radial population density. So it's r times the radial population density, which is going to be 15 times 1 plus r squared to the -1/2 power dr. So this is the population that lives between 10 and 30, lives in the ring between those two values. 15 is a constant, so I'm going to push it out front. So 15 times the 2 pi that's there is 30 pi. We have 30 pi integral from 10 up to 30. And this would be of r times 1 plus r squared to the negative 1/2 dr. I think I'm going to need to use u substitution for this, so I'll set u equal to the inside of the negative 1/2. So I usually want to choose u to be kind of the inner part of the function. Then du will be integral of 1 is nothing. Integral of r squared is 2r dr. So I have the dr and the r. I need a 2, so I'll put a 2 in here, which if I put a 2 in there, I have to divide this by 2. And so what I get is 30 pi over 2 is 15 pi. I'm going to get new limits of integration because I'm swapping out to u's now. I'll have u to the negative 1/2. And 2r dr is du, so 2r dr becomes du. To get my new limits, I put, let's do 10. 10 squared is 100. 100 plus 1 is 101. When I put 30 in, 30 squared is 900 plus 1 is 901. So we are down to here. When I integrate this, it's going to go to u to the positive 1/2. When the half comes down, I need a 2 out front for that to cancel. So we'll get 15 pi, and then we'll have 2u to the 1/2 power evaluated from 101 to 901, which we can say 2 times 15 is 30. So it's 30 pi u to the 1/2 power, which 1/2 power, that's actually square root. So we can write it as that just to make it a little cleaner. Of 101 up to 901. Oops. So when we calculate that, we get 30 pi square root of 901 minus 30 pi square root of 101, which we could, I guess, simplify a little bit further as 30 pi times square root of 901 minus square root of 101. And we'll see, okay, what is that about equal to? We'll round to the nearest person, I guess, because this is going to be a population, so we don't want, like, halves of people or whatever. And we get this is about equal to 2,000 people, we'll say. Or actually, the book says 1881. I guess they rounded down, so we'll round down like the book. And since the units were thousands, this will be 1,000 people. The actual number was like 188.1.825, and I guess 0.825 is not actually another person, so we don't count it as another person. So we'll say 1,881,000 people is how many people live in that ring. Okay. So the next bit we have here is talk about laminar flow, which basically says if you have a pipe or a tube or something that fluid flows in, the fluids close to the wall, they have friction with the wall, so their velocities will be kind of slow. And the fluid's a little bit away from the wall. They bump into the slower fluids, so they move a little bit faster, but they still don't move super fast because this is slower moving stuff. And as you get to the center, your flow increases. So laminar flow basically is the distance away from the center of the pipe due to wall friction. The slower the flow velocity or the water flow or fluid flow is, it flows fastest through the center and slowest up against the wall. So what we're going to do here is they give us a formula for this. So they tell us the flow rate. So this is kind of the next example we're going to look at. They tell us the flow rate Q is going to equal 2 pi integral from 0 up to r. And they give us r, the velocity with respect to r, dr. So this has the same format as the radial density function, but instead of being population density here, this is now velocities that depend on how far away from the center of the pipe you are. So for our example, it's going to be based off of this. We say the velocity of a blood flowing through a vessel of radius r centimeters. So the velocity of blood flowing through a vessel of radius r centimeters is, so here's our velocity equation, v of r equals some constant k times r squared minus little r squared, where little r squared is the distance from the center of the vessel. Or little r is the distance from center of vessel. Okay. In this problem, they want us to find the flow rate, which they'll say is Q, as a function of R. And they give us that K is equal to 0.5 inverse of centimeter seconds. Okay. So setting this up is pretty easy. They're asking us to find the flow rate. So we say Q. The units of the flow rate, since we're dealing with centimeters, and the flow rate in terms of centimeters would be cubic centimeters, and this is per second. So we're going to say the flow rate's units will be cubic centimeters per second. We'll just kind of keep that in our brain right now. But we're basically going to integrate, it says for a radius of capital R, so we integrate from 0 up to R, of R times our velocity function. K is 0.5 times R squared minus little r squared, and we're taking the integral with respect to little r squared. So the 0.5 I'm going to push out front. It will hit the 2, and those will cancel out and just leave you a pi out there. This r I'm going to distribute to the capital R squared and the little r squared. So we'll get capital R squared little r minus little r cubed from that distribution. Okay, now I think we're ready to integrate here. So we'll get pi. R will go to 1/2 r squared, so we'll have r squared times, let's see, this will be 1/2 r squared, so that'll be little r squared over 2, minus r cubed is going to go to 1/4 r to the 4th. Evaluate that from 0 up to capital R. So let's go through and do that. We get pi times, see, this would be r squared, capital R squared times capital R squared, which is capital R to the 4th over 2 minus 1/4 capital R to the 4th. So that's capital R to the 4th over 4. Then we would have minus pi times capital R squared times 0 squared over 2 minus 1/4 times 0 to the 4th, which that whole term is just 0. So this will say pi r to the 4th over 2 minus r to the 4th over 4 will be r to the 4th over 4. And this is a flow rate, so that'll be cubic centimeters per second, and that will be our flow rate in that situation. Okay, so we're down to calculating the average as an integral. So we're going to define this and the next thing will finish up this section. So we say for this definition, we say the average value of an integrable function f of x on a to b is we get average value equals 1 over b minus a, integral from a up to b of f of x dx. Okay, so this problem here, next problem is going to be pretty straightforward from this definition. This is example 7. They want us to go through and they want us to find the average value of f of x equals sine of x on the interval 0 up to pi. And if we kind of think about this, you find the average of something, you add a bunch of the, you add how many there are together, and then you divide them by the total number of things you added. So the adding them together is kind of, the integral is kind of synonymous with that. And then dividing them by the total number there were. B minus a is the integral length, so you divide it by the integral length, and that gives you the average value. So when we go to do this problem, we just basically use the formula above us to set it up. We say, all right, this will be 1 over pi minus 0. That'll be the length of the integral. We integrate from 0 up to pi. The integral we're trying to calculate is sine of x dx. And this right here will tell me the average value. So that is the average value that it's asking us to find. So this will equal 1 over pi, integral from 0 up to pi of sine of x dx. When you take the antiderivative of sine of x, so there's 1 over pi out front still. Sine of x goes back to negative cosine, so we get negative 1 over pi cosine of x. And we want to evaluate it from 0 up to pi. So we use fundamental theorem of calculus part 1. We get negative 1 over pi cosine of pi minus negative 1 over pi cosine of 0. Okay, so let's see here. Cosine of pi is negative 1. So this is negative 1 over pi times a negative 1, which is positive 1 over pi. Minus a negative is positive. Cosine of 0 is 1. So 1 over pi times 1 is plus another 1 over pi. 1 over pi plus 1 over pi is 2 over pi. So that would be the average value of that function over that interval. And that's basically all there is to that one. All right, so we're going to do the final thing is just writing down a different format of the mean value theorem. So this will be the last kind of statement. We have theorem 1. This will be the mean value theorem for integrals. So what this theorem says is if f of x is continuous on interval a up to b, then there exists a value c, which is also an element of the interval, such that f of c is going to equal 1 over b minus a, integral of a to b, f of x dx. So that's kind of rephrasing the mean value theorem. We'll put some more examples up here, probably on Monday or Tuesday, that kind of deal with how does some of the stuff look like on the AP test. But we're going to stop there for this one.